Hello, everyone. Welcome to our final design review. My name is Jacquelyn Rader, and my teammates are Jennifer, Jana, Aldo, and Steven. And today we'll be talking about our project, which was the solid fuel design and performance. For this project, our advisor was Dr. Santner, and our client for this project was California State LA Eagle Rocketry team. To begin going over the agenda of this presentation, we're going to first start off with some background information. We will then dive into the fuel team, which will be conducted by Jen and Jana, and a little bit of Aldo as well. And they will just be going over the composition of the fuel, the fabrication process, and results from the simulation software. We will then be going into the test stand and fuselage team, which comprised of Aldo, myself, and Steven. And in those slides, we will be discussing the test stand design and manufacturing process, along with the data acquisition and ignition system, and the fuselage design and manufacturing process. After that, we will then be discussing future work and the conclusion of the project.
So a solid rocket propellant is a rocket with a motor that uses solid propellants that are mainly composed of a fuel and oxidizer as the means of propulsion. A simple solid rocket motor will consist of a casing, a thermal insulation, a grain, nozzle, and igniter. So a solid fuel oxidizer mixture will be inserted into the rocket, and then this usually has a cylindrical hole at the center, and then an igniter will be used to combust the propellant surface. A hot exhaust will be choked at the throat and exits the nozzle producing thrust. So early solid fuel rockets in the 13th century were powered by gunpowder and were used for warfare on China. Solid rockets are still used today in military applications, such as missiles, low-performance rocket models, and strap-on boosters for launching vehicles. And then NASA Space Shuttle solid rocket booster has been used for primary propulsion on a vehicle that was used for human spaceflight, and it provided the majority of the space shuttle's thrust during the first 2 minutes of flight.
So one of our main problems that we were trying to fix during this entire project was the manufacturing of the solid propellant. As you can see on the photo on the left, that shows voids and cracks and bubbles in the end result. So that was one of the issues that we were trying to fix and avoid in our project.
All right, so in regards to the requirements in our project, we were to improve upon the Eagle Rocketry solid fuel propellant recipes. In addition to that, we're tasked to develop several recipes in order to test those through non-destructive testing. In other words, a static fire testing. And in addition, we were to also develop the manufacturing process in order to provide these solid fuels and have them cure it in our situation here. Furthermore, and with respect to the fuselage and test stand team, we are to design a reliable, reusable, and safe fuselage and test stand. In addition, we were to design a data collection system that will be able to measure the thrust and the burn rate. And finally, we were to implement an ignition system in order to ignite the rocket fuel during the static fire test.
So this project was divided into two teams, the fuel team and the test stand and fuselage team. The deliverables for the fuel team were to understand or develop an understanding of solid fuel and its manufacturing process, to create 5 or more recipes depending on the variables that we want to test. And we wanted to divide each of those recipes into grams based on the mass fraction of each ingredient. We want to determine the manufacturing methods that are appropriate for each fuel, and to develop non-destructive testing for each fuel once it's a finished product, and to run simulations using software to determine the performance of each fuel.
And the deliverables for the test and the fuselage team consisted of designing a sand that will safely contain the rocket during ground testing. The design of fuselage must be reusable for multiple testing. Also, to improve the SolidWorks design of the fuselage to fit a safety factor, and create an ignition system that will simultaneously collect thrust and burn time during testing, and also to perform hydrostatic and static fire tests.
So now we're going to dive into the solid fuel subteam, which consisted of Jana, Aldo, and myself. So obviously, as I mentioned before, it's possible as the propellant is curing to obtain voids and cracks in the final product, as seen in the photo on the right. So the chemical composition of the fuel is very important. But even more important than that was how it was manufactured and the process and steps that we took. Eagle Rocketry had previously used continuous mixing, which had led to some bubbles in the propellant. So one way that we fixed that, or tried to fix it, was to use batch mixing, which was more repeatable in the end product. And so far it has worked well for us.
There are two types of solid or composite solid rocket fuel. The first type would be aluminum powder as the fuel and ammonium perchlorate as the oxidizer, and the second type is black powder carbon as the fuel and potassium nitrate as the oxidizer. We opted to use aluminum and ammonium perchlorate in our fuel.
So of course, one of our important aspects of the project was freestanding grains, and we did cartridge loading, which went along with our batch mixing. The cartridge inside of the fuselage was made of cardboard that we were able to insert into the fuselage, and once it was dried and formed, we could also take it out of the fuselage so that we could reuse it to make other propellants. So this is done under a fume hood at Cal State LA, and luckily we were able to get a few of them done. And it's important that it's done under a vacuum or inside of a vacuum, because that helps to suck out any extra air that is inside of the propellant. And we're currently researching a vacuum to use in the fume hood at school.
The manufacturing process for solid fuel begins with the mixing process, and we start mixing the dry ingredients, which in our case was the aluminum powder, the ammonium perchlorate, and in some cases the iron oxide. And then once those ingredients were mixed, we added the wet ingredients, which were the binder, the curing agent, and in some cases a plasticizer as well. And then once those ingredients were mixed into a substance with a doughy consistency, we would pour them into the mold for the casting process, and then we would leave it in the fume hood for the curing process.
And the curing process normally lasts 1 to 2 days, around 80 degrees Fahrenheit. And luckily, the days that Jana and I were mixing the fuel, it was warm outside, so we didn't need a heater or anything. And of course, curing in a vacuum is best to avoid the air bubbles. And one of the other objectives for our project was to have low density, to produce a propellant grain-free, no cracks, and no low density areas, and no other flaws.
Another objective of the fuel team was to run simulations using software, and we decided to compare the results of a software we paid for and the results of a free option as well. The software we paid for was called thermochemistry, and the free alternative was using ChemKin. And we wanted to compare the two to determine if using ChemKin was a viable alternative to using a simulation software that we had to pay for.
So this table is a breakdown of each of our fuels by percentage of each chemical. So we have used as Jana had said, ammonium perchlorate, aluminum powder, and iron oxide. Those were our powders. And HTPB, PBAN, MDI, epoxy, and IDP as our liquid mixing. And as you can see, each fuel has 70% of ammonium perchlorate, and all of them but one have the same amount of aluminum powder. We did this for sake of consistency to see if we were to alter the percentages of any other of the chemicals to see if we can see trends in each of the propellant or discrepancies in the propellant. And this table was made out of the thermochemistry simulations that I was doing. It's broken down into each propellant, and out of all the propellants, you can see that propellant 3 and propellant 4 seem to be the best in terms of our characteristic velocity, which is the C star value, and also the specific impulse value that they each gave us. But for the simulations, we were lucky to also obtain the burning temperature and the density and the molecular weight.
So when we used ChemKin, one of the problems we ran into was that thermodynamic data was not available for some of the chemicals that we were using, and these chemicals had to be broken down into smaller species whose data we did have access to. We assumed initial conditions to be room temperature and atmospheric pressure, and we guessed at the equilibrium conditions, and we guessed those conditions to be 1500 Kelvin and 1000 psi. And we used a text file that included the molar fraction data of each chemical species, and we imported that data into ChemKin. So one of the species, or one of the chemicals that we didn't have thermodynamic data for was epoxy, and I had to draw out the chemical structure of this ingredient and break it down into smaller species based on this chemical structure, and then I used these the thermodynamic data of each of these species in ChemKin. And this is what one of the molar fraction input files looks like.
So we plotted results for the flame temperature at a range of atmospheric pressure all the way to maximum pressure inside the combustion chamber during the fuel combustion. And it was observed that the fuel 1 will combust at lower equilibrium pressures, while the fuel 4 combusts at higher pressures and higher temperatures. ChemKin simulations at the end do not have the highest of accuracies in the flame temperature values, since the fuel 3 was expected to reach higher flame temperatures in comparison to our other software simulations. And we assume that this was perhaps due to the fact that we were limited on the thermodynamic data available to us for the ChemKin results.
So the photo on the right is Jana and I last week when we were mixing fuel in the fume hood. We were able to get three propellants mixed actually, and hopefully this week we can go and see if the our most recent recipes withstood what they were supposed to withstand. We decided to do fuel 1 and 2 because fuel 1 has iron oxide in it, so we wanted to see how it would perform based on the instead of the other fuels. And everything was weighed on a digital scale inside of the fume hood, and the dry ingredients were mixed first, and then we would mix in the wet ingredients and mix it until it was a dough battery consistency, and then pour it into the fuel mold. And then these are some pictures on the right. I believe that's Jana's hands holding the cardboard filled with our fuel. And then on the left, That's a picture of the cart. This is before it was even loaded. And the rod actually goes inside of the fuel so that we're able to put a little ignition wire inside of the fuel, and then it burns more uniformly.
All right, so since results were obtained using software simulations, there we are expecting possible future testing, and where the thrust will be measured mechanically. And in the following slides, we'll present the model that will be used by the test and fuselage team. So as for the test net, an important aspect in static fire testing is to evaluate the rocket motor's ability to produce thrust. And this will be done by manufacturing a test stand that will allow for static fire testing by providing a structure in which the fuselage will be ignited by an ignition system and thrust be measured by a thrust measuring system. And the test stand will be designed in a way where static ground testing should be safe for students and reliable for multiple testings. Now, as for the design of the test stand, the rocket motor housing will consist of using a 12-inch aluminum pipe and an aluminum flange that will serve as a base for the rocket housing. The inner diameters will allow for the fuselage to be inserted upon testing. The housing will be fixed onto a wooden table where a digital weighing scale of 70-pound capacity will be used to measure the rocket motor thrust. And then here are the visuals for the testing table and the digital weight scale to be used. Now, as for the assembly, the testing assembly will consist of a weighing scale that will be resting on the second level of this table. And then a hole of approximately 2 inches will be cut where the fuselage will go through and will rest on the weighing scale, and then exert a downward force upon ignition onto the scale, and this way measure the thrust generated by the fuselage. The rocket will be ignited at the top of the end where the nozzle is at, and then this will be done using an ignition system that will be further explained.
Moving on to the thrust and ignition system, we will firstly be talking about the thrust measuring system. To begin with, we initially had design plans to use a remote to ignite the rocket, for which things got delayed. And so we had to kind of improvise a little bit using a scale as shown previously in Aldo's slides regarding the test stand. And it'll be placed once again on the second layer of the test stand. And the goal for this is just to measure and record thrust or the force that's being applied on the scale. And the way we're going to do this is by setting a camera fixed to the scale, and from there kind of manually inputting data into Excel to collect our information and produce graphs and data that we need and require for this project. And so that is hopefully going to be our goal when we set up the thrust measuring system in real life. Moving on to the igniter system, the materials that are going to be required are the nichrome wire, masking tape, aerogloss, and paper clip. And you can see the process for that in the images below. How this is overall going to be set up is we're going to be placing the end result of this igniter into the nozzle of our project, and using nichrome wire and an igniter wire, we're going to extend it out where we're able to ignite it from a safe distance without being in harm's way. And so once again, during actual static fire testing, we're hoping to be able to incorporate this in our igniter system. Yeah, so our overall goal for this project is once again to safely ignite the rocket so that the fuselage, so that way we're able to collect data. And this is our end goal that we're hoping to achieve, is just by once again having that wire extending outward, once again at a safe distance. That way we're able to safely kind of do this static fire testing. And hopefully this is what the end result will look like.
Okay, so in regards to the fuselage assembly, we were able to do some simulations via SolidWorks that will allow for us to get more ideas on what dimensions we should be designing the fuselage in and what forces we should be considering. So here you can see a cross-sectional view of a static pressure test that was conducted via SolidWorks. These red arrows here on the picture depict pressure that is being applied radially outward on the interface of the combustion chamber. So this pressure was set to be 1000 psi. And in addition, in order to replicate the real life scenario of what is actually going to be going on, more explained later on, we have a force of 100 pounds being applied on this top end of this cap here. We call this a bulkhead. And in addition to that, we're also putting a fixed end on the outer radius of this top nose. And so this simulation was conducted analyzing the factor of safety of this design here. So the factor of safety here would be 2.3. So that's a factor of safety. We were shooting for a factor of safety of 2, and we ended up getting a factor of safety of 2.33. So that allows for us to have some room for extra material in order to, if we need to, add on to the dimensions or the thickness of the fuselage. So knowing the simulations via SolidWorks and the data there, we were able to come up with some dimensions. In addition to that, we received a blueprint of the original fuselage that was used from Eagle Rocketry. We scaled down those dimensions, and then we were to where the fuselage was about 8 inches tall. And then we conducted the SolidWorks simulations in order to see what our factor of safety was. So this is the result here. This is our blueprint of the fuselage here. And this is the product at which the end result for the machining here. We can see the fuselage here. The material selection here is aluminum 6061-T6. So one might ask, what's the purpose of the fuselage? So the main objective or the main purpose of the fuselage is to provide a sound housing or a sound structure to house the solid fuel. Not only that, but the fuselage is multi-purposed. So here you can see in the picture, and which we'll discuss later on in the presentation, there's a nozzle that is being attached through these inner threads that are being aligned inside the fuselage. So the nozzle is connected inside the fuselage. On the other end here, we have a bulkhead that is, in other words, like it's another word for a bulkhead. You can consider it as just a cap. So it's a cap on the bottom of the bulkhead that will allow for just for everything to be secure on that end. So the purpose of the fuselage, once more, is just to provide a sound structure for the fuselage, the the nozzle, and the bulkhead. Moving on forward, here more specifically, we have the bulkhead. So the purpose of the bulkhead is to have a sound piece of material that is sealing the one end of the fuselage. So we'll be discussing this a little earlier, is that this bottom face of the bulkhead that's the face that's going to be applied on the scale in order to measure the weight, and that's going to be used to calculate the thrust. So that piece of material needs to be thick enough in order to withstand all the forces and or the thrust that is it's encountering on the during the static fire testing. In addition to that, we do have this bulkhead is connected to the fuselage by the use of threading. So we do have inner threads right along inside the inner lining of this bulkhead, and it's just screwed on there, attached to the fuselage. Continuing on forward, so with respect to the nozzle, so I'd like to go into more details on how we arrived at the throat area and the exit area. And so there's some equations that we do need to consider in order to arrive at an efficient nozzle. So there's an equation known as the optimum expansion ratio. So this equation allows for us to find a ratio between the throat area, the cross-sectional area of the throat, which is specified here, this dashed blue cross-sectional area, and the relationship between the area of the exit nozzle, depicted here on the figure on the right. And so we use this equation that allow for us to figure out the optimum expansion ratio. And some assumptions that I used on this equation were that the K value, which is otherwise known as the ratio of specific heats. So this is, we concluded that it would be using it, we're just estimating here, so we're having a ratio of 1 for a K value. PE, that means the pressure of the exit area. So in other words, the pressure of the atmosphere upon the nozzle exiting out into the regular atmosphere, we have that as 1 atmosphere. And the pressure on the inside, in other words, PVO, would be 64 atmosphere. So this is an estimation of what we believe before I had the data run by the solid fuel team. So I estimated at 64 atmospheres. So the result of this equation gave us an optimum expansion ratio of about 7.3. Now, in addition to that, I was advised by my advisor, Dr. Santner, to scale down that optimum expansion ratio to a ratio of 5. In order for that ratio to be scaled back up into the Eagle Rocketry's full-scale model on their fuselage. And so in more explanation, so given the optimum expansion ratio of 5 here, we're able to figure out the optimum exit diameter. And so in order to calculate the optimum exit diameter, we do input the ratio between the area of the exit cross-sectional area and the cross-sectional area of the throat. Now, this is given, we know that. We want it to be 5, right? In addition, we do have one given value, which is the diameter of the throat area, which is 0.4 inches. And in addition, the area of the throat, which is 0.13 inches. We plug these values into the equation to find the nozzle exit diameter, and we arrive at an exit diameter of 0.9 inches roughly. And so that allows for us to change the specific diameter of the exit area, in which will allow for an optimum expansion ratio of 5 there. Moving on forward, so this is our design of the nozzle here, in which shows the converging and diverging geometry of the nozzle. So as a result of manipulating or finding the optimum exit diameter, this angle, 21.1 degrees here, that angle does change. And so now this angle it regulates depending on what our optimum expansion ratio will be. So thankfully we settled on a ratio of 5, and then we move forward on with the project. So here you can see the finished product that was machined here with the converging geometry here, and also the exit throat, the exit diameter, which is here depicted by the diverging geometry there. In addition, I would like to state that the nozzle, the bulkhead, and the fuselage were machined by Blake downstairs in the ECST machine shop.
Moving on to our future works in which we're hoping to achieve within the coming weeks. We have first the hydrostatic tests, which would be done the week of May 3rd. We also are hoping to do the static fire tests, which would be done the week of May 3rd or May 10th, depending on our manufacturing progress. By that point, we're hoping to have actual data to analyze, for which we will do that on May 12th. And finally, with that data, finalize our report and results and discussions. And that would be done the week of May 12th.
And just to recap a little summary of our project, we were able to make 3 propellants at school, and hopefully this week we can complete 2 more, and hopefully we will be able to static fire test them sometime in the next few weeks.
Now, in regards to the test stand and the fuselage team, we were able to develop a safe, reusable, and reliable test stand. Now, this test stand will be proven during the static fire testing, wherever the manufacturing has been completed. Now, in addition, the reason why we still have the planned fuselage studies is that we're still going to be conducting a hydrostatic test on the fuselage to ensure the structural integrity and making sure that it's a reliable fuselage for safety reasons. This is why it's still on the planned stages. Now, in continuation, we do have the data collection system and the ignition system that have been completed and awaiting for static fire testing.
So we would like to acknowledge our senior design advisor, Dr. Jeffrey Santner, who has worked with us through this project by providing us with useful resources and ideas. Blake Cordes, who has helped us manufacture fuselage parts, and Jonathan Cervantes, who has also helped us manufacture our parts at the makerspace. The Eagle Rocketry liaison, Amy Mora, who we had frequent communication, and finally, Steve, who supplied material for this project. And then here are our references for our project and also for the future work slides.
Thank you.